Hello, welcome to today's lecture. The topic of discussion today is understanding GPU bottlenecks for machine learning. And today we are going to discuss the sources of inefficiency that arise when using the GPU for machine learning applications. For this, we'll have to take a look at the architecture of the GPU and how it differs from the CPU. We'll also discuss the abstractions and concepts needed to reason about GPU efficiency. So GPU accelerators are expensive devices and they are very powerful as well. Let's say we procure state-of-the-art H100 GPU costing an enormous amount and with a peak throughput of several of teraflops per second. And when we get this piece of hardware, we expect that now we can accelerate our training by a lot. But the reality is that we are only able to utilize a fraction of the compute capability of this device. And we have brought this device expensively, but we're not able to use it to its peak capability. What are the causes of the inefficiency when running machine learning applications on GPU? And how can we overcome these inefficiencies? To understand this, we will have to dig a little deeper and understand how the GPU looks like, how is it designed, and how it functions. If you are only able to get something like 10 to 30% of the peak compute capability of a GPU, which is not so uncommon if used naively, it's not just a concern that maybe training will take a bit longer. It has a cascade of, it creates a cascade of problems, and the consequences that result, they are quite, in a way, they are quite serious. So the first has to do with cost. So either we are renting these GPUs on the cloud, which means that, let's say if the utilization is only 20%, it means that every 1,000 rupees I'm giving to the cloud provider, basically like wasting 800 rupees out of that. So it can blow up the cloud bill significantly if we don't take care about how well the GPUs are utilized. Even if we don't use cloud GPUs and have it on premises, what often happens is that because these pieces of hardware, they are so expensive, then they tend to be shared across multiple projects and multiple teams. And if my project, if training my model is taking significantly longer, it means that there are other people waiting in the queue and their work is getting delayed. So it has consequences from that perspective as well. It also means that probably my training run is going to take a longer time. And with the scale of models we are currently working with, the delay can be of the order of weeks and months. And with this delay, we are able to iterate much more slowly. When developing machine learning models, it's always an iterative process where we try out with a few different architectures and hyperparameters. And if each iteration is very expensive, particularly because the GPU is not utilized well, then it means that I won't be able to try out a lot of different things and the quality of the final model may not be so as good. And finally, if you are using GPUs for longer because they consume so much of energy, it means that the electricity bill also goes up significantly. And it's not just about the GPU consuming electricity, also it creates heat, and then the cooling infrastructure also takes up cost. And the problem of GPU inefficiency is magnified at scale. With the large scale transform models, which we are working today, consider a scenario where if I'm able to use the GPU at 50%, which is a good rate, then let's say training a foundation model takes 1 month. So we are not just talking about one GPU, it's probably a cluster of GPUs acting together in this case. And if the utilization is somewhat poorer, at say 25%, it takes me 2 months to train. And at 10% GPU utilization, which is quite poor, it takes me 5 months. So for a company to spend this much amount of time, like 5 months with poor utilization of GPU, it means that the economy won't work out well for them. And also it's just with the timelines and with how the market works, it will be very infeasible for them to launch a model like this. To understand efficiency or inefficiency, we really need to reason when reasoning about a machine learning program. We can think, where does it spend time? And there are basically three important components. The first is how much amount of time is being spent doing computation on the GPU. The second is how much amount of time is being spent transferring tensors within the GPU memory, and everything else is overhead. So first of all, we'll start off our discussion by focusing on the overhead aspect, because it really touches upon how the GPU and the CPU work together in a heterogeneous computing environment. So typically, when we run our PyTorch code, it executes on the CPU. The GPU is hooked on to a system managed by the CPU. And the CPU runs the code and it identifies, or rather we specify the portions which are math heavy and which can be parallelized, and we offload those computations to the GPU. So for instance, when the interpreter sees torch.matmul, it ends up launching an operation called a kernel on the GPU, which does matrix multiplication. And here in the system, we have two different processors, and they have different characteristics and different architectures. And we have linked them up with a memory bus, which is typically PCIe bus, which is somewhat slower. So we have what we call a heterogeneous computing environment, where we have multiple processors whose architectures are quite different, and we want this system combined to work efficiently. Let's take a closer look at how the architecture of the GPU differs from the CPU. The architectures of these processors really were determined by the kind of workloads that they're supposed to run. So CPU runs general purpose, general processes, whether it be the operating system, databases, browsers. And here, the focus really is on interactivity. So the response time needs to be slow. And because of this, the design of the CPU emphasizes low latency. On the other hand, the GPU was initially designed for graphics application, to render frames in graphics applications. And rendering frames requires doing a lot of floating point computations per frame, and also transferring a lot of data from the main memory to the GPU cores. So we have a lot of compute and a lot of memory transfer per frame. There's another aspect with the GPU as well, that the kind of computation which has to be done per frame, that is such that it can be thought of as doing the same mathematical operation but on multiple pieces of data. And the designers of the CPU, they went for this logic that we are going to run a lot of threads in parallel. All of those threads will be simple. They'll run the same sequence of operations on different pieces of data. Whereas for the GPU, the threads look much simpler. Now, looking at these two diagrams of the high-level architecture, on the left, there are multiple cores in a CPU, and what we are seeing here is a representative diagram where, let's say, the control units of all the cores, they have been coalesced together and shown all together. So really what we need to think when looking at this diagram is, what are the relative sizes of these boxes which I'm seeing? So when seeing the CPU and the GPU, the elements are really the same. There's control, there's ALU, there's cache, there's DRAM, there's memory connections, but it's in how complex these individual components are and how much of emphasis in terms of chip area and power was given to these individual components that really determine the differences in the CPU and GPU architecture. Let's take a look at these one by one, starting with control. So because CPU threads, they can have more intricate logic, And also, for the purpose of minimizing latency, we do some more sophisticated processing of instructions, such as maybe branch prediction, out of order execution, and so on. So, because of this, the control unit tends to be more complex, and as a result, it also tends to occupy more area on the chip. Whereas for the GPU, I have a lot of smaller control units, and these were designed with the idea that these have to manage threads which kind of have very simple sequence of instructions. And because they don't focus so much on minimizing latency, so they didn't have to care so much about branch prediction or out of order execution. So overall, the chip area given to control is less. When it comes to the ALU, we have a smaller number of these units for the CPU. Each of them, they are what they try to do is for any instruction, let's say for multiply, for divide, for anything, they try to make it go as fast as possible. So they really try to minimize the instruction latency. And because of this, they also are more complex than their GPU counterparts. As a result, each of these ALUs, they are in a way more capable than their GPU ALUs, but I have a fewer number of them only because they are more complex. It means that they take up more area on the chip and also more power. So, but by the way, for the GPU, I have a lot, like almost maximum of the chip is devoted to the ALU units, and each of these they are simpler, and as a result, they are also smaller. So I have a lot of them altogether occupying a significantly more area of the chip. CPU caches, there are more levels to the cache hierarchy, and they're also bigger in size. And really what they help us do is they minimize the memory access latency. And this is a core concern of the CPU to be able to minimize these latencies. And a lot of chip area is devoted to these large multi-level caches. Whereas the GPU, it does have cache, but really it is more tolerant in a way of memory access latencies. We'll see later on that this is fine for the aim of the GPU of maximizing throughput because it is able to hide these memory access latencies because of a large number of threads. And because of this, each thread probably has more latency as compared to the CPU, but taken together, the throughput which I get from the GPU is much higher. I have been talking about threads, and what do they mean? Threads are distinct streams of instructions, and each thread is scheduled to run on a different execution unit. The CPU thread I've tried to show it's a bit longer and thicker because I wanted to emphasize that CPU threads, they are more complex in nature, and also they have a longer lifespan as compared to the GPU threads. Now, there isn't really an analogous unit to what we call GPU threads on the CPU. Instead, it's more meaningful to compare the CPU threads with what is called a unit called a warp on the GPU. And warp is a group of 32 threads. The reason why I'm making this analogy is because all the 32 threads in a warp, they run the same instruction at any clock cycle, but on different pieces of data. And it is not the individual threads within the warp which are scheduled and descheduled, but rather it's the warp which is either scheduled to run or is put into sleep mode. And that's why it's more helpful to think when comparing with the CPU thread to look at the GPU warp. Now, as I've been saying, let's think about a database application. A multi-threaded implementation of that would have a significantly more complex logic than the kind of threads which run on the GPU. The threads on the GPU have a short sequence of instruction and they carry it out and they're gone. So they really have a very short lifespan when compared with the CPU threads. The CPU threads can run for much longer period, like when the application is alive. In a way, the CPU threads can be alive. Whereas the GPU works do very specific application and then they're dead. An important difference between CPU thread and WOBs is the way they are scheduled. So CPU threads are managed by the operating system, and the GPU WOBs are managed by a piece of hardware called the WOB scheduler. And anything which is managed by the hardware, it usually goes much faster than something which is managed by the software, which is the case for the CPU. The amount of overhead involved when switching to CPU threads, that's much higher as compared to the overhead involved when swapping GPU works. And this has to do with the fact that the state of a thread, it's saved on registers, and we only have enough registers that once a thread is put to sleep, we often have to save the state of a thread to memory. Whereas for GPU, I have more than enough registers so that when I'm putting a worm to sleep, I don't necessarily have to transfer its state to its main memory. So they can lie on the registers. So effectively, we say the GPU works, they have almost zero overhead when being scheduled. And by means of an analogy, we can compare a low latency system with a system focused on high throughput. So I borrowed this analogy from this excellent talk, which I recommend you visit. Let's say we are going from place A to place B. And here I have shown two locations in New Delhi, the Secretariat and Dwarka. If you were to take a car on, let's say, early morning when the roads were empty, it would take you, let's say, 45 minutes, which would be quicker than what the time you would spend taking the metro between these locations. So when taking the metro, we have to go to the station, and then we have to wait for the metro to arrive. The metro stops at intermediate stations, and then we get down at our final points. In a given unit of time, the metro is able to transport a much larger number of people as compared to what a car does. So, in this sense, we can think of the metro as a throughput-oriented system and the car as a latency-oriented system. So, the car is designed to get me from point A to point B as quickly as possible. Now, if we have traffic on the road, the travel time might be significantly higher than what I've shown here. And this points to another feature, or rather a limitation of latency-oriented system, that let's say if I have a lot of cars on the road, which corresponds to maybe I have more threads in my system, and each of these threads, they are more complex than their GPU counterpart. So in a way, it clogs up the system because the overhead involved in switching between threads and managing these threads is much higher than what's true for GPU. So I can't oversubscribe my latency-oriented system with more number of threads the way I can do for a throughput-oriented system. And this notion of oversubscribing with a large number of threads, that really is a key pillar of how GPU computing works. By means of specifications of two state-of-the-art systems, a GPU and a CPU, let's verify this notion. Looking at the peak throughput, NVIDIA H100 GPU, it can do 34 teraflops per second. And this processor, it does 4.3. The GPU is about 7 to 8 times faster than this processor. In terms of the memory bandwidth as well, the bandwidth in the GPU is almost 10 times higher as compared to its CPU counterparts. But when it comes to the latency of getting something from the DRAM memory, from the main memory, for the CPU, it's much smaller as compared to the GPU. And we do see that what matters for the GPU is I want to do, for every frame, I want to do a lot of floating point computations, and I want to transfer a lot of things from main memory Whereas for the CPU, I want to make one thread go as fast as. And because of these differences and on CPU and GPU characteristics, we have to think about overheads quite a lot when reasoning about GPU and thinking about this heterogeneous computing environment. So here's our Tonic PyTorch program where we are doing 5 matrix multiplication on relatively small matrices. And as we said before, that when PyTorch sees this, then it does some processing, after which it's able to instruct the GPU. So here in this diagram, the top part I'm showing by the CPU and the bottom one is by the GPU. And when PyTorch running on CPU sees this, it does some processing and it submits an operation called the kernel to the GPU. And because the GPU is so much faster than the CPU, it's quickly done with that. The CPU, on the other hand, it is launching these sequence of jobs one after another. What we see here is that the launch time is significant because the CPU is so much slower than the GPU. And these overheads, they really are a result of the Python interpreter, the PyTorch framework, and also the overhead involved in launching the CUDA kernel. So it's really the difference in speed between the CPU and the GPU, which kind of makes this problematic because here we have a lot of periods when the GPU is idle, and we don't want this because it's terrible for GPU efficiency. We really want to see the GPU fully maximized here so there are no gaps. So as long as PyTorch can run ahead of the GPU kernels, these framework overheads in launching the kernel, they can get hidden away. And for this to happen, our GPU operators need to be big enough. So for instance, here I have made the matrix sizes from 100 to 10,000 by 10,000. And in this case, the GPU computations, we are hiding the launch overheads of the CPU. The problem is that it's not always easy to make these individual kernel computations large enough. It's apart from matrix multiplications, which we'll discuss later on, it's not always possible for all operations to take significant amount of time. This problem is hard as the GPUs increase in capability with newer architectures because they get more powerful and it's harder to keep them occupied. And we'll talk about these ideas a bit more in later lectures. How do we find out whether we are in a regime where the CPU overhead is dominating or whether we are in a regime where the GPU computation has hidden the CPU overheads? One way is to, let's say, if instead of multiplying matrices of 100 by 100, if I make it 200 by 200, then these GPU kernels will take a bit longer, will take maybe twice or 4 times. Anyways, it will take longer for it to execute. But even then, our total execution time would be dominated by these CPU kernels. So we can try to increase the problem size by a factor of 2 and then see if our runtime has increased proportionally. If not, then we are bounded by the CPU overheads. Whereas in this case, if we were to make the GPU kernels maybe have 2x more compute, like maybe take double the time of execution. So overall execution time would also in a way double. Another way is to use a profiler. And here it's the output of PyTorch profiler. The top part is showing the computation happening on the CPU and the bottom part is on the GPU. So this axis is increasing in time. And in this first case, we see that there are gaps between the kernel computation on the GPU, and we can infer that we are bounded here by the overhead, by the CPU overhead. Whereas in this case, the kernels are big enough that the CPU scheduler, it submits jobs to the GPU faster than the GPU can compute them, which is good. So the first challenge of GPU program is avoiding CPU bottlenecks and keeping the the GPU busy, and we really want the GPU to be the bottleneck. So once we have optimized the CPU part of our program to a point where the profiler shows us that the GPU is the bottleneck, then we can look at the other components where our machine learning program is spending time. And the other parts are it's spending time to compute and doing operations on the GPU. And it's spending time transferring things in GPU memory. Consider a simplified model where a function is reading some input from memory, it performs math operations, and then it writes its output to the memory. Let's denote by Tman the time spent doing memory operations. So by this I mean transferring things from the main memory of the GPU to the GPU cores which do the execution. And Tmap is the time spent doing the math operations. So the time our program will take on the GPU, so here we don't talk about the CPU overheads, we're just focusing on the GPU. The time our algorithm will take to run on the GPU, that will be bounded by these two quantities. The lower bound is the maximum of these two quantities. And this is because here we are assuming a model where the memory operations and the math operations, they are perfectly overlapping. So in this case, the execution time will be greater of whichever of these two quantities. On the other hand, if we assume that there is no overlap between memory operations and compute operations, then our execution time would look something like the sum of these two quantities. And typically, when working with the GPU, we are somewhere nearer this regime as compared to this. So we do have a significant amount of overlap between memory and compute. Maybe let's talk about the source of that. Because we have a large number of GPU threads, so if one thread is waiting for some piece of data to arrive from memory, another thread, so that particular thread which is requesting for memory access, it's put to sleep and another thread is made running. In this way, I can hide my memory access time and in a way use most of my time for compute. Because we have a large number of threads, we are able to do a lot of overlapping of this memory and compute. And also the compiler also, when it looks at the sequence of instructions, it tries to rearrange things in a way so that the loads they can happen as early as possible in the compiled program. So because of these two factors, we do have quite a significant degree of overlap of these. If our math operations, they take more time than the memory accesses, then we say that we are in compute bound regime. So the time which it takes for our algorithm to run, it mostly is limited by how fast the GPU can do the math processing. Whereas for the other case, we are spending most of our time transferring things around in memory rather than doing math computation. So we are in a way limited by the bandwidth of the GPU memory from what's called the high bandwidth memory to the GPU cores. And really we want to be in this regime where it is the GPU is spending most of its time doing math rather than being limited by memory transfer. For the case of full overlap, this one, in case we are compute bound, then the execution time will be Tmath because it's the max of these two quantities. Whereas if you are memory bound, the total execution time will be Tmemory. And we are going to discuss this scenario of full overlap, partly because this is what's closer to what happens in the GPU in reality, but also because the analysis works out to be simpler for this. How much time is being spent for math and how much time is being spent for memory, that is also still useful. Consider this process where A and this A region in red is denoting the area let's say, for memory accesses, and B is the time spent doing math computation. If I made the math computation faster by 5 times by, let's say, having a faster processor, overall, it wouldn't change the execution time of the algorithm as much as, on the other hand, let's say if I decrease the memory accesses by half and I don't change the math computation time here. Thinking about PMath and PMEM, even for a case when we don't have overlap, that can serve as a guide for where we should focus our optimization efforts on. So in this case, I will have most gain if I focus my optimization on making either the memory accesses faster or maybe requesting less things from memory if possible. Now let's focus on the case of full overlap. In the compute bound regime, the math operations take more time than the memory ones. These things, they can be measured for a program, but even looking at an algorithm, we can find out these quantities. T-math is basically how many floating point operations, let's say, how many floating point operations are involved in that algorithm, and then the rate at which those operations can be performed, which is given by the peak throughput of the GPU. The memory T-mem is how many number of bytes will I have to transfer from the main memory to the GPU cores divided by how fast is the bandwidth. And when thinking about this, like we are not thinking about memory caches. And yeah, so it's just like there's the main memory on one side and then the registers on the other side. We can rearrange this inequality to have this on the left-hand side, the number of, for a particular algorithm, how many number of operations it's doing per byte of data transferred to or from memory. On the right-hand side, we have this quantity. What is the peak throughput my GPU is capable of? And what is my bandwidth? This quantity is called the arithmetic intensity of an algorithm. And it's a property of the algorithm. It's measured in flops per byte. The right-hand side, it's a property of the GPU, the hardware device. And this is called the ops byte ratio. This quantity tells us that for every piece of data, for every byte of data I'm getting from memory, how many operations is my algorithm doing? What we want to do is, because we know that when GPUs have evolved, their throughputs have improved at a much higher rate as compared to the bandwidth. So really, this is where like the bottlenecks really lie. So what we really want is, for every byte I'm getting from memory, if I can do a lot of operations on the GPU, then in a way I can keep the GPU cores as busy as possible. And this quantity is telling me what is the minimum number of operations needed to do per byte of data transferred to be able to keep the GPU fully busy as possible. Diagrammatically, the arithmetic intensity of our algorithm can lie anywhere on the spectrum. The ops byte ratio of the GPU is a point on the spectrum. If our algorithm happens to have more arithmetic intensity than this threshold, then we are in the compute bound regime, which is good. If our arithmetic intensity is such that it's less than the ops byte ratio, then we are memory bound. And we have a few choices here. We can do things like kernel fusion or quantization so that we move less things around in memory. This will be, and because of that, when we move less things around in memory, we can nudge our algorithm more and more to the right in terms of arithmetic intensity. These kind of ideas to improve the arithmetic intensity of an algorithm so that it's less memory bound will be the topic of our later discussions. Let's see how can we get the ops byte ratio for any GPU. And this really has to come by looking at the data sheet of the GPU. Let's look at the data sheet for the H100 GPU. And this is the data sheet for the H100 GPU. And here, for the bandwidth, so we need the peak throughput and the bandwidth. The bandwidth number is clearly given, 3.35 terabytes per second. For the throughput, the picture is a bit more complex. There are a lot of numbers given, and what we see is that there is a variation in the data type which has been used. So how many bits that particular data type is using, and it's either 64 bits or 32 bits, 16 bits or even 8 bits. And then there's also a difference between, are we asking the GPU to do normal, ordinary operations, or is it specifically, are we asking it to do matrix multiplication? So let me look at the throughput for operations on floats, 32-bit floats, for general purpose operations. So 67 teraflops. And the aspect ratio in that case is 67 teraflops per second divided by 3.35 terabytes per second, which is 20. So we can see that we can have a toy diagram of the GPU where there's execution units of the GPU running at this capacity. And then there's the main memory of the GPU, which can send data at this rate. And what we want to do is we want to think about sending data as fast as possible so that my GPU compute can remain completely busy. So think of the GPU compute as a consumer and the main memory as a supplier. So I want to supply things fast enough so that this consumer is kept as much busy as possible. So an aspect ratio of 20 is, it's not always easy to achieve. So for every byte of data which I get from main memory, I have to do 20 operations. And FP32-bit is 2 bytes of data. So if I'm transferring a 32-bit number, it means that I have to do 80 operations on that to, in a way, keep my compute fully utilized. And there aren't a lot of algorithms which require us to do 80 operations per every piece of data, per every value we obtain from memory. So we can see where do the kind of operations which you do in a neural network, they fall into certain categories, and where do they lie on the spectrum of arithmetic intensity, and are they memory bound or compute bound? Let's start with element-wise operations. So they act on each element of a tensor individually. An example of this would be ReLU activation. Thinking about, let's say, reasoning for 16-bit floats, for instance. What I need to do is I need to read X from memory. I need to do this computation, and I need to store the result of this computation back to memory. So the arithmetic intensity of ReLU is one operation, one max operation, which is one instruction. And the denominator, I have transferred 4 bytes. I've read 2 bytes for X from memory, and 2 bytes I have written, which is the output. So the arithmetic intensity is 1/4, which is quite low. And this also holds for other kind of non-linearities occurring in neural networks, be they sigmoid or tanh, be they scaling operation or bias, and so on. And all of these are characterized by low arithmetic intensity. And as a result, they tend to be memory-bound operations. Another class of operations which occur in neural networks are what we call reduction. So they operate over a range of input values to return one output value. An example is the max pooling operation. The output image. So here I am doing max pooling on 3x3 window with unit stride. As a result, my input and output, they will have the same dimensions. Let's look at one particular 3x3 window over which max pooling will happen. So the operation will compare all these nine values, return the max of that, and place it in this particular output coordinate. And the arithmetic intensity of max pooling, it ends up being 2.25 flops per byte, which is more than 0.25, which we saw for ReLU, but still it's less. And yeah, so this also is less. Now to see how we arrive at this number, the way to do it is that let's fix our attention to one particular number, one particular pixel in the input image. From the perspective of this pixel, This particular pixel will be involved actually in 9 pollings. We will slide around this polling window to the right, to top, bottom, and so on. So this particular pixel X will be here once this window slides in this direction, this, and so on. Basically, this input value of X will participate in 9 polling operations, and polling will involve one max operation where X will be involved. So basically, the max poll is doing max over these 9 values. So it can take max over all of these. So because X is participating in 9 polling windows, we can say that there will be 9 operations, floating point operations, of which X will be a part of. So we are thinking in FP16, we needed 2 bytes to bring in X. And because the output has the same shape as the input, so there will be an output value corresponding to the input as well. So where X is located, I need to send back the result, the output value at that pixel location back. So 2 bytes read for X and 2 bytes for the output at the same location as X. This is one way of doing this computation. You can also consider a larger grid and in a way total up, account up all the pollings happening and so on, and all the memory reads and all the memory writes, and you will arrive at the same figure. Max pooling is one type of reduction, but also batch normalization and even softmax. All of these are examples of reduction. So these are very common in neural networks. And all of them, they are characterized by low arithmetic intensity and they are memory bound. Now, convolution is also, theoretically speaking, convolution is also a reduction operation. It also operates upon a window and produces an output value. But I'm going to consider it separately. I'm going to club it together with matrix multiplication because the way convolution is implemented, it can take advantage of the fast matrix multiplication ability of the GPU in a way other reductions like max pooling, they are not able to do. So I'll consider convolution with matrix multiplication. So matrix multiplication, which will be the core algorithm for us. Let's say we are multiplying 2 matrices in FP16 format. Their shapes are m by k and k by n, resulting in an output matrix of shape m by n. And we can think of matrix multiplication as a collection of vector dot products to get the 0, 0 coordinate of the output. You can think that it's in a way a dot product between the 0th row of my first matrix and the 0th column of the second matrix. For this output value, how many operations did we have to do to get this? If we say that there were key elements, there are key elements in this vector, we had to do k multiplications and then k minus 1 additions for these. So for a single output value, we did these many number of operations. For the overall matrix, it will be m times n times. So these are the total number of output numbers. And for each number, we did 2k minus 1. Let's say that we ignored the 1 factor, 2 times m times n times k, approximately speaking, the total number of operations. And this is fine for us because we are considering somewhat larger matrix sizes. So it's okay for us to ignore this one here. What about the number of bytes which were read in and which were written in this matrix multiplication? I needed to read in the data corresponding to these 2 matrices. So I had m times k numbers here and k times n numbers here. So total of these many numbers. And for each of them, because these are in FP16 format, so I read in 2 bytes. And then once my output matrix is there, then I have to write that back. And that means writing m times n numbers of 2 bytes each. And so the arithmetic intensity of this matrix multiplication happening in FP16 is this quantity, m and k. So this goes in the numerator and this in the denominator, and this. So When thinking about is our matrix multiplication compute bound or it's memory bound, we need the ops byte ratio of the GPU. And we saw from the data sheet, let's go back again. So we saw from the data sheet that I have the bandwidth number, but the throughput is different depending on what sort of data type I'm using and also whether I'm doing matrix multiplication or not. So because for our case, we are right now looking at FP16, so we are going to consider this number. We are also considering tensor core because we are looking at matrix multiplication right now. Now notice that here there's a star and it says that this we are able to achieve this throughput when the matrix is being multiplied as sparse. And it's given later on that if these matrices are not sparse, then we achieve a peak throughput which is half of this value. And that is the figure we are going to use when thinking about are our dense fully connected layers compute bound or memory bound. The tensor cores can give this much throughput for FP60 with sparsity. So for our case, the ops byte ratio we have is we have half of this peak throughput. We are doing matrix multiplication, so we can look at tensor core, but our linear layers, they are fully connected and they are dense. Effectively, the throughput is, as the datasheet says, it's half of this. And the bandwidth is this. The opt byte ratio is this number, which previously was 20, which we had looked. But in the case of reduced precision, matrix multiplication, it is closer to 300 flops per byte, which is huge. Can our fully connected layers, which effectively do matrix multiplications, can they have an arithmetic intensity which is close to, which exceeds this? So let's consider a linear layer whose inputs have dimensionality 1024 and whose outputs have dimensionality 4 times of that, so 4096. Let's consider the batch size of 1. In this case, M represents the batch size, K is their input dimension, and N is the output dimension. So finally, I get back the result, batch size times the number of output dimensions. And hence we are memory bound. But if we increase the batch size to 512, then our arithmetic intensity is approximately 315 flops per byte, and we are more than the ops byte ratio, and we are in the compute bound regime. So this is good. So this really points out that it's one way to keep the GPU busy is to have it solve problems of computations of large sizes, which in the linear layers, it means to have larger batch sizes. This is fine to get better efficiency, but we are also not able to do this, like not able to increase the batch size significantly because the memory requirements, when we increase the batch size, that also increases linearly with respect to the batch sizes. So we have the activations, we have to save the gradients and so on. So all of this, it increases with the batch size. And because my GPU memory, so we saw that in the first lecture we spoke, that also tends to be a critical resource. So it means that it's not always easy for us to increase the batch size to a point where we can enter a compute bound regime. And this also highlights a point about this discussion of arithmetic intensity and ops byte ratio is that all of this analysis is really in a way rough calculation, thumb rule, because here we are not considering, for instance, the caches of the memory cache of the GPU. Then we also in our accounting, we're only thinking about how many arithmetic operations are happening. But oftentimes, when an instruction is executed, there are other things as well which happens before and after arithmetic operations, which has to do with fetching instructions, decoding instructions, and so on. But those things, they are not coming into the picture here. So this is really like a rough calculation, but it's still quite useful. Convolution as well, consider a patch of the input image here. So it's a 3x3 window and the convolution with this Fredo. And the final value which I'll get is this. So I1 multiplied by F1 plus I2 multiplied by F2, I3 by F3, and so on. And then I sum them up. And this can be thought of as a dot product between this mix. So this patch, if I flatten it out, and if I flatten out this filter, then this quantity, the output which I desire, it's basically the dot product of these. So just as we thought of the matrix multiplication as a collection of dot products, convolution also can be thought of as collection of dot products. So it's collection because this filter is slided over the whole input image. So we have many dot products which we have to do. And the same kind of logic is also holds true for convolution as well, that if the problem sizes are big enough, then we can be in the compute bound regime. So let's place our algorithms which we have discussed on the spectrum which we saw before. This is arithmetic intensity here, increasing arithmetic intensity. This is the critical point, the byte ratio of the GPU. Element-wise operations in neural network and also a lot of reduction operations like max pooling and so on, they tend to have low arithmetic intensity and then they tend to be memory bound. For matrix multiplications and convolutions, if the problem sizes are small, they end up being in the memory bound regime. But if we can make them large enough, then we are in the desired regime of compute bound. So with that, initially see that GPU, they are not optimized for latency and they are more tolerant of latency in memory access. So here, I said that it's most useful to think of in terms of these units called warps, which are basically groups of 32 threads, because these are the units in which like threads are scheduled and put to sleep. So looking at a particular warp, it's a combination of some parts which do computation, so sequence of instructions which do compute. Then there's an instruction which requests for memory access. And because memory access, like it has such a high latency, and the GPUs, they don't have complicated caches to minimize this latency. So it takes a long amount of time before this data to arrive. And then the computation happens at the warp. And when the first warp has requested for a memory access and it is waiting, because the GPU is designed in a way that I can have a lot of warps running at the same time. And also because there is almost zero overhead in scheduling warps. So I can quickly put this warp to sleeping and make the second warp running. And when the second warp waits for memory access, it schedules the third warp, and so on and so forth. So in a way, if we scan along this time axis, we will see that in this part here, all of the time, we have been doing computation. There have been times the warps have been waiting for memory to come, but the GPU execution units, they have also been kept busy by computation. At this point, the data for warp 1, it has arrived and it is now running and so on. And once it is done running, then warp 2 is ready to run and then warp 3 is ready to run and then they are run one after another. So because we can have a lot of warps, so we can be more tolerant of the high memory access latency because we're able to hide the latencies with the computation. That's all for today. In the next lecture, we are going to talk about the CUDA programming model and the abstractions which are necessary for us to think, how do I make this algorithm? How do I implement in a way so that it can run efficiently on the GPU? And this will require us to go a little more deeper into the GPU architecture. Thank you.